I'm your host, Jackie Mullins, and welcome to From Cells to Us. How? The podcast where we figure out how life went from a single cell to complex creatures like us. Last episode, we watched Luca's kids move out and go their separate ways. Bacteria went one direction, archaea went another. They colonized every corner of the planet. They swapped genes like they were in a genetic commune, and they ruled the Earth for over 1 billion years. Life was thriving. Prokaryotes everywhere. Horizontal gene transfer making evolution fast and chaotic. Everything was going great. And then something happened that nearly ended it all. One group of bacteria figured out a new trick, a way to capture energy from sunlight. And in doing so, they started producing a waste product, a toxic, corrosive, deadly gas. Oxygen. Yes, that oxygen. The stuff that you're breathing right now, the stuff that keeps you alive, that oxygen was once poison, a pollutant, a weapon of mass extinction. Today, we're talking about the Great Oxygenation Event, the day life invented photosynthesis and accidentally poisoned the planet, the first mass extinction, and how the survivors learned to not just tolerate oxygen, but use it. This is the story of how a catastrophe became an opportunity. Let's get into it. Now, to understand why oxygen was such a big deal, you need to understand what Earth looked like before it showed up. Early Earth, and we're talking 3 to 4 billion years ago, and actually I'm going to do a sidebar here really quick. You might be annoyed with me because it seems like I keep saying 3 to 4 billion years ago, but we have to remember how long 1 billion years is. I feel like because there are billionaires and the US is in like $38 trillion of debt, the number of billion kind of gets normalized, if you know what I mean. So a quick recall on just how huge 1 billion years is. First off, there are 1,000 millions in a billion. 1 million is a huge number, but take 1,000 of them, and that's 1 billion. Okay, let's try minutes. 1 million minutes ago, that's about 2 years. We were just getting out of our post-pandemic era, doing great. 100 million minutes ago, that was the 1830s. Abraham Lincoln is a young man. There are people alive who knew the founding fathers. 500 million minutes ago. Medieval times, nights, plagues, no thank you. 1 billion minutes ago. We're at around 100 AD. The Roman Empire is in full swing, and I'm asking you to think about 3 to 4 billion years ago, not minutes, years. So take everything you just felt, scaling from 1 million to 1 billion minutes, and now replace every single one of those minutes with a year. It's unhinged how crazy a time scale that is. Homo sapiens have been around for about 300,000 years. That's 30% of 1 million, or 0.03% of a billion, or 0.007 of Earth's history. We have existed for essentially nothing, a rounding error, a smudge on a screen. So when I say hundreds of millions of years go by, that can all happen in the span of 1 billion years. I'm sure you all know that, but a quick reminder is always nice. All right, sidebar over. Back to early Earth, 3 to 4 billion years ago. There was almost no free oxygen in the atmosphere. Like basically zero. The air was mostly nitrogen, carbon dioxide, methane, maybe some ammonia. Not exactly breathable by our standards. And that was fine. Life didn't need oxygen. Remember, the first cells were anaerobic. They made energy without oxygen. They used other chemicals, sulfur, iron, hydrogen, whatever was around. Think of them as the MacGyvers of the microbial world. No oxygen, no problem. They looked around at what the early Earth had to offer, and they were like, sulfur? Sure. Iron? Let's go. Hydrogen? Don't mind if I do. Just absolute survivors, making it work with whatever they could find. Oxygen would have been the problem, actually. For these early cells, oxygen was toxic. It's highly reactive. It wants to steal electrons from other molecules. And that's great if you're evolved to handle it. But if you haven't, Oxygen rips your cellular machinery apart. So, for the first billion years or so of life on Earth, everything was anaerobic. No oxygen, no problem. The atmosphere was thick with methane and carbon dioxide. The sky probably wasn't even blue. It might have been orange or, just hazy. The oceans were full of dissolved iron, giving them a greenish tint. Just take a second and picture that orangish sky with green oceans really quick. I mean, it doesn't look like the Earth we know it. And it isn't. It was a very different world, but a world where life was doing just fine until something invented photosynthesis, which is just using sunlight to make energy, what our plants and trees do today. Enter cyanobacteria, sometimes called blue-green algae, though they're not actually algae, they're bacteria. These little guys figured out something revolutionary: how to use sunlight to make energy, aka photosynthesis. Now, photosynthesis wasn't entirely new. Some earlier bacteria had figured out simpler versions, using light to help make energy but not producing oxygen. We call this anoxygenic photosynthesis. But cyanobacteria, well, they took it to the next level. They figured out how to split water molecules using sunlight, just tearing them apart like splitting firewood. The axe is the sunlight, and the wood splitting is the H2O molecule. So they took water, H2O, add light energy, and they split the H and the O apart. The H, the hydrogen, well, they used that to make sugar for energy. But the O, the oxygen, well, they just kind of dumped it out, like we should all do with the extra screws and things we get from making IKEA furniture. Just throw them out, guys. You're never going to use them. This is oxygenetic photosynthesis, the kind plants do today, the kind that fills our atmosphere with oxygen. And let me tell you something about oxygenetic photosynthesis. It was incredibly efficient. Cyanobacteria could make way more energy than their competitors. And in the game of life, if you're thriving, you spread, you multiply. However, in this instance, as they are spreading and multiplying, they are also pumping out more and more oxygen as a waste product. It's kind of like if someone invented a super efficient car, but the exhaust was nerve gas. The drivers are like, oh, I am saving so much money. And everyone else is like, yeah, but you're killing us. And the driver shrugs and just starts counting his money. So, great for the driver, not so great for everyone else. So cyanobacteria were pumping out oxygen, but the atmosphere didn't immediately fill up with it. Why? Well, Earth had oxygen sinks, things that absorbed oxygen before it could accumulate in the atmosphere. Kind of like how a sponge absorbs water until the water starts spilling out. The biggest sink? Iron. Remember how I said the early oceans had lots of dissolved iron? Well, oxygen loves iron. When oxygen meets iron, they react. It's love at first sight. They're immediately moving in together against all their friends and family's advice. The iron oxidizes, which just means it rusts. And as the iron oxidizes, it falls through the water as solid iron oxide. For hundreds of millions of years, this is what happened. Cyanobacteria made oxygen. Oxygen met iron. They held hands, and the iron rusted and sank to the ocean floor. Now, what's amazing is we can actually see this in the rock record. There are these formations called banded iron formations, layers of iron-rich rock alternating with other sediments. They're found all over the world, and they date to this period. They're literally the rust from billions of years of oxygen meeting iron. So the oxygen was being produced, but it was getting soaked up by all that dissolved iron. The atmosphere stayed oxygen-free for hundreds of millions of years. But here's the thing about sinks, they can fill up. Eventually, after hundreds of millions of years, the iron ran out, the sponge filled up, and Earth's cup runneth over. And just to clarify, iron didn't completely run out, But the easily accessible dissolved iron in the oceans did get used up. I mean, there's still iron today. But suddenly there was nowhere for oxygen to go. So it started accumulating. In the oceans first, then in the atmosphere. This happened around 2.4 billion years ago. So let's think about that timeline. Cyanobacteria started producing oxygen about 3 to 4 billion years ago, and it took all the way to 2.4 billion years ago for the oxygen to start accumulating. That is a very large amount of time. And this transition into a new world, well, there's a name for it. We call it the Great Oxygenation Event, or sometimes the Great Oxidation Event, or my personal favorite nickname, the Oxygen Catastrophe, which is the name life living at this time would have named it. Because make no mistake, for most life on Earth at this time, this was a catastrophe. Remember, almost everything alive was anaerobic. They had evolved in a world without oxygen. They had no defenses against it, and suddenly this corrosive, reactive gas was everywhere. It's like if the air you breathed your whole life was suddenly replaced with something else entirely. Imagine waking up tomorrow and the atmosphere is now 21% chlorine gas. You have no defenses. Everything that made you successful is now useless. Everything alive would just start dying. Oxygen was a death sentence for anaerobic life. We don't know exactly how many species went extinct, but it was probably most of them. This is the first mass extinction in Earth's history, and we barely talk about it. I want that to sit with you for a second because I think it's wild. Oxygen, the thing we need to survive, the thing we associate with life and health and fresh mountain air, was originally a pollutant, a waste product, a toxic gas that killed almost everything. It reframes everything. And the cyanobacteria, well, they weren't trying to poison the world. They're not a Bond villain, a little bacteria in a suit drinking a martini, chuckling menacingly as they dump oxygen out as their waste product, telling everyone who will listen about their plan to wipe out all life on the planet as they know it. No, they're just doing their bacteria thing, making energy from sunlight, dumping their waste. They had no idea they were causing the apocalypse. And this happens all the time in evolution. One organism's waste is another organism's catastrophe, or eventually another organism's opportunity. We are eventually cyanobacteria's waste recipients. Because here's the thing about mass extinctions. They clear the board. They remove the dominant players. They open up space for new strategies, new innovations, new ways of living. I kind of picture this like the fall of Rome. Rome was dominant. Rome had the whole board locked up. And when it fell, yes, it was chaos. Yes, it was catastrophic for a lot of people, but it also created a vacuum. And into that vacuum stepped new kingdoms, new languages, new cultures, new ways of organizing society that never would have had a chance while Rome was still running the show. The fall of Rome didn't end civilization. It reshuffled it. Evolution works the same way. When the old giants fall, the world suddenly has room for new experiments. That's exactly what the oxygen catastrophe did. Anaerobic life was Rome. It had dominated this planet for billions of years. Oxygen came in and toppled it. And into that vacuum stepped something new, something that could not only survive in this toxic new world, but thrive in it. Now, the oxygen catastrophe was terrible for anaerobic life, but it set the stage for everything that came after. And it literally set the stage. Oxygen allowed for more ATP, more energy, so bigger, more complex life could exist. Oxygen set up the ozone layer, essentially sunscreen for the entire planet, blocking the UV radiation that would have murdered anything trying to live on land. Now, how this happened is when oxygen accumulated in the atmosphere, which they did as O2, UV radiation from the sun hit those oxygen molecules and split them apart into single oxygen atoms. So just an O, no more two. But lo and behold, those single atoms then bonded with intact O2 molecules. And these formed O3 molecules, known as ozone, or as I like to call it, the third wheel molecule. The ozone just happens to be really good at absorbing UV radiation. It's like when Thor lightninged Iron Man in his suit, just zapped him when they weren't friends. When it was done, Iron Man's suit was powered up to like 1,000%. UV radiation zapped oxygen, which accidentally created a planetary defense system. Full defense mode activated. And oxygen opened the door to a whole new kind of metabolism, aerobic respiration, which is so much more efficient than what came before. It's literally almost unfair. It's like upgrading from a bicycle to a Ferrari. Anaerobic life was doing fine on a bicycle, putzing along, staying in their own little neighborhood. But oxygen handed certain organisms the keys to a Ferrari, and those organisms, well, they took off. They didn't want to stay in their little neighborhood anymore. They had places to be, and now they had the power to get there. Everything you are, every cell in your body, every breath you take, every thought you're having right now runs on that Ferrari. We are quite literally the descendants of the organisms that figured out how to not just survive the apocalypse, but thrive in it. Okay, let's just take a breath real quick. An oxygen breath, obviously, and recap where we are. Early Earth had basically no oxygen. Life was anaerobic, no oxygen, and doing just fine. Then, cyanobacteria showed up, invented oxygenetic photosynthesis, and started pumping out oxygen as waste. For hundreds of millions of years, the oceans soaked it up. All that dissolved iron rusting and sinking to the ocean floor, which we can still see today in banded iron formations. But eventually, the iron ran out. The sponge filled up and oxygen started accumulating in the atmosphere around 2.4 billion years ago. And it was a catastrophe. The first mass extinction in Earth's history, most anaerobic life, gone. But something new is on the horizon. And let's talk about what the survivors did and what oxygen is still doing to you now. So, oxygen is everywhere now. Most anaerobic life is dead or hiding. Now, what happens next? Some survivors, they retreated. They found places where oxygen couldn't reach, deep in the mud, in the guts of other organisms, in isolated pockets. Their descendants are still there today. That's why we still have anaerobic bacteria. They're hiding from the apocalypse their ancestors barely survived. Now, this is a lot like when the asteroid wiped out the dinosaurs. The giant dominant creatures, gone. But small mammals that could burrow, hide, or wait out the apocalypse, they survived and eventually inherited the Earth. And, spoiler alert, those small mammals, well, we're related. So the next time you listen to Destiny's Child, I'm a Survivor, just think about how far back that statement really goes. But other survivors did something more interesting. They adapted. Some developed defenses against oxygen, enzymes that could neutralize it before it did any damage, antioxidants, ways to handle this reactive molecule without dying. And then someone even further, they figured out how to use oxygen. So instead of, like karate chopping it away, instead of putting up barriers to keep oxygen out, they invited it in and they put it to work. See, oxygen is reactive. That's what makes it dangerous. And it's still dangerous. Like, have you ever seen signs on the hospital or senior housing doors about the warnings that there is pure oxygen in that room? No smoking signs are everywhere. Well, that's because pure oxygen environments are extremely flammable. Hospitals have strict protocols because even a small spark near pure oxygen can cause explosions. Oxygen doesn't burn itself, but it makes everything else burn faster and hotter. But reactive also means energetic. If you can harness that reactivity instead of being destroyed by it, you can extract way more energy from your food. This is aerobic respiration, using oxygen to burn fuel. And I've been talking about what oxygen did to the planet, but let's zoom in for a second and talk about what it does to you. Channel your inner Carrie Bradshaw. And as I heard about the first mass extinction, I couldn't help but wonder, what does this mean for me? So, specifically, every time you take a breath, what's happening in your cells? Well, it all comes back to mitochondria. And mitochondria, let's say it together, is the powerhouse of the cell. Yes, we all learned that, and everyone believes it's been so helpful in April for mitochondrial season. Yes, that is a tax joke. Schools, why don't you teach about taxes? Anyway, here we are. Your mitochondria are why you need oxygen at all. Every breath you take is essentially you feeding your mitochondria. You're not feeding you, you're breathing for them. You are just an elaborate oxygen delivery system for a tiny cellular power plant. But what are they actually making with all that oxygen? Well, ATP. ATP stands for adenosine triphosphate, which is a mouthful and completely unhelpful as an explanation. So let's just ignore that and talk about what it actually does. So every single thing your body does, it requires energy. Thinking, breathing, blinking, your heart beating, your cells dividing, all of it. And your body doesn't just run on food directly. You can't just shove a sandwich into your bicep and expect it to work. Your body has to convert that food into a universal energy currency that every single cell can actually use. That currency is ATP. Think of it like this. Food is like a $100 bill. Useful, but you can't put it directly into a parking meter or a vending machine. You need to break it down into something every machine accepts. ATP is quarters. It's the universal currency your cells actually spend. Every time your cells need to do something, contract a muscle, fire a neuron, build a protein, they spend ATP. And when the ATP is spent, it needs to be recharged. So your cells are constantly making more. Every single second of your life, your cells are churning out ATP like a tiny mint that never closes. Okay, back to ancient Earth, where mitochondria have not evolved yet. So now let's talk about why oxygen was such a game changer for this time. Aerobic respiration, using oxygen to burn fuel, is way more efficient than what came before. Like 16 times more efficient. With anaerobic cell burning glucose, it gets about 2 ATP. That's like $2 an hour for a full day's work. An aerobic cell burning the same glucose, that's about 32 ATP. That's $32 an hour versus $2 an hour. I know which one I'm casually evolving towards. Now that jump wasn't just a numbers upgrade. It was the difference between your cells scraping by on pocket change and suddenly having a full wallet. More energy meant more options, more complexity, more life. Oxygen didn't just help life survive. It gave life the budget to get ambitious. And honestly, it's just like humans and actual money. You don't see a person living paycheck to paycheck doing much other than survive. But people who have a little extra, I mean, heck yeah, that's the blank check kid throwing a Velcro trampoline in his backyard. That's Richie Rich sending acidic toothpaste to get his butler out of jail. You have energy to spare and suddenly you can get creative. The survivors who figured out how to use oxygen didn't just survive, they thrived. They were earning 16 times more than their predecessors. They had more energy than anyone else. They could do more, grow more, move more. What was once a poison became a superpower. So I have to jump out of the ancient world again and ask a question that regards us as humans who breathe today. Because I keep telling you oxygen is poison. It was the apocalypse. So did oxygen ever completely stop being a poison? Kind of creepy question, right? And the answer might surprise you. I kind of feel like clickbait now, but no, oxygen has never stopped being oxygen. It's never stopped being a poison, and it is slowly poisoning you right now. We figured out how to use oxygen. We built incredible machinery around it, but oxygen never stopped being reactive. It never stopped being dangerous. We just got really good at managing it. Now, here's what I mean. When your cells use oxygen to make energy, the process isn't perfect. It's a little messy, as processes tend to be. And some of those oxygen molecules get only partially processed. They become what are called free radicals. New band name, I call it. But free radicals are actually just an oxygen molecule with an unpaired electron, which makes it unstable and aggressive and desperate to react with whatever is nearby. Much like that person we all know who can't be single, like as soon as they're single, they're looking for their next attraction. But in this scenario, they are toxic. Whoever they get with, they bring them down too. They damage them. They're not bringing good energy into this relationship. They are, in fact, slowly destroying their new partner, which in this case is your DNA, your proteins, your cell membranes. That's not great. Free radicals are essentially tiny wrecking balls bouncing around inside you right now, and over time that damage accumulates. Your cells can't quite keep up with the repairs. Things start to break down. This is called oxidative stress, and it's one of the leading theories for why we age. And here's the thing, none of this kills you immediately. It's not dramatic. It's not a single catastrophic event. It's just small damage accumulating quietly over decades. Your cells have repair mechanisms, and they're genuinely remarkable, but they're not perfect. And as you age, they slow down. And eventually the damage starts outpacing the repairs. It's like someone sneaking into a factory at night and slightly bending all the tools. Nothing breaks immediately, but over time, everything starts working a little worse, a little slower, a little less precisely. That's aging at the cellular level. Aging is just the damage winning, and the diseases linked to this oxidative stress, cancer, Alzheimer's, heart disease, diabetes, basically every major disease of aging has oxidative stress somewhere in the story. So the oxygen that powers every single thing you do is also slowly and quietly contributing to every major way your body eventually breaks down. That's the bad news. However, there is some good news, everybody. As Dr. Farnsworth would say, remember those chaotic, can't-be single free radicals. Well, it turns out that they have a therapist. And that therapist is antioxidants. Those antioxidants everyone keeps telling you to eat, vitamin C and E and all those superfoods, they exist specifically to neutralize free radicals. Think of them as sliding into the situation and donating exactly what the free radical is missing, that unpaired electron, that desperate unmet need. Antioxidants fill it. And suddenly the free radical calms down, no longer missing anything, no longer destructive, crisis averted. Your body has been running this therapy program since the moment you were born. Every antioxidant you eat is essentially paying for another session. There's always a catch when you go from a $2 an hour job to a $32 an hour job. Am I right? The poison never went away. We just learned to live with it, until we don't. Now, just one more wild thing about oxygen and you are technically on fire right now. Not metaphorically. You didn't just hit 3 shots in a row in NBA 2K. Yes, the first one. Yes, I played it on my cousin's Sega Dreamcast. But literally on fire. Here's what I mean. What does fire do? It takes fuel, adds oxygen, releases energy. That's it. That's the whole chemical reaction. Your cells do the exact same thing. Take fuel, food, add oxygen, release energy. Same reaction. Chemically identical. And I know what you're thinking. Jackie, that seems like a stretch. I believe you're editorializing a little here. But I promise you it's not. Write out the chemical equation for fire. Fuel plus oxygen produces or equals CO2, water, and energy. Now write out the chemical equation for what your cells do. Fuel plus oxygen produces equals CO2, water, and energy. Identical. Chemists will back me up on this. The reason it feels like a stretch is because fire and breathing seem so very different. But that's just speed. That's it. Same reaction, different pace. So why aren't you just a walking bonfire? Well, because your cells do it incredibly slowly and carefully. Fire just lets everything go all at once, one big chaotic explosive release. Your cells do the same thing, but in teeny tiny controlled steps, capturing a little energy each time. like lighting one match at a time instead of dumping a whole bag of charcoal on the flame. That's what your enzymes are doing, running a controlled explosion at 98.6 degrees, which is insane when you think about it. And this is actually why you need to eat. Your body needs fuel to combust. No fuel, nothing to burn, no energy. You're a fire that goes out without wood. And this is why you need oxygen. You literally cannot run the reaction without it. Hold your breath long enough and your cells start running out of the key ingredient, just like a bonfire. You ever get yelled at by the self-proclaimed fire master for stacking the logs wrong and smothering the fire? That's just because you cut off the oxygen. No oxygen, no fire. Same thing happening in your cells. Cut off the oxygen supply and the whole reaction stops. And when you breathe out, that's CO2. That's your exhaust. That's the smoke from your internal campfire. You are genuinely a very slow, a very organized, a very well-dressed combustion engine. Yes, Alicia Keys and Katniss really are the girls on fire, but you are too. Just one that learned how to do taxes, although not through school, obviously. Okay, back to ancient Earth and the oxygen catastrophe. You've thought you heard all oxygen has done, but wait, there's more. The Great Oxygenation Event didn't just kill a bunch of anaerobes, it might have frozen the entire planet. So let's recap what the Great Oxygenation Event has done so far. It's poisoned most of the life on Earth. It triggered the first mass extinction in Earth's history. And now, just to really, drive the point home, it might have frozen the entire planet. Yeah, here's how. Before the Great Oxygenation Event, Earth's atmosphere was full of methane. Methane produced by all those anaerobic bacteria just doing their thing. And methane is a powerful greenhouse gas, which means it traps heat. So early Earth was actually being kept warm by a blanket of methane. And then oxygen showed up. Oxygen and methane, well, they do not get along. They react. But not like iron and oxygen, where they yell, Katarina and Arturo, and sink to the bottom of the ocean. No. Oxygen and methane are a different story completely. This was Mount Vesuvius versus the people of Pompeii. Oxygen, or Mount Vesuvius, absolutely obliterated methane, or the people of Pompeii. So oxygen moved in and took over and became the new dominant force in the atmosphere. And the methane blanket? Dismantled, ripped apart, gone. And when you remove the thing that was keeping the entire planet warm, well, it gets cold. But not just a little cold, because here's the thing about ice. Ice reflects sunlight. Instead of absorbing heat, it bounces it back into space. So as temperatures dropped and ice started forming, the ice reflected more sunlight, which dropped the temperatures further, which formed more ice, which reflected more sunlight. And you see where this is going. It's a runaway feedback loop with no brakes, a thermostat that only knows one direction. This is what they started to call snowball Earth. And if you want a modern example of methane as a greenhouse gas, you can think of cows. Cows burp and flatulate methane out consistently as a byproduct of their digestion. It's the same deal as the ancient anaerobic bacteria. Just organisms doing their thing, processing their food, dumping their waste. No ill intent, just, cow vibes. And yet it's contributing to warming the planet. Same principle, methane traps heat. Back then, that heat was keeping Earth from freezing. Today, that heat is doing the opposite of helping us out. Cyanobacteria, cows, same energy, different era, different problem. And maybe you're like, what the heck, oxygen? Where were you on this one? Yes, oxygen is reacting with and destroying atmospheric methane today, same as it did back then. But we're producing it so fast that oxygen can't keep up. Remember the iron sink? It's the same idea, just flipped. So the bucket is filling faster than it's draining. Anyway, back to the frozen planet. So the Great Oxygenation Event didn't just change the atmosphere. It may have literally iced the entire planet. Oxygen came in, killed most of the life, and then tried to freeze the rest. Oh, Dennis, what a mess. Absolute menace oxygen was. Okay, but Eventually, things stabilized. The ice melted, oxygen levels found a new equilibrium, life adapted. So how did the Earth just thaw out? Well, volcanoes. Unglamorous, reliable, absolutely free-for-all volcanoes. They just kept erupting under all that ice, pumping CO2 into the atmosphere. And CO2 traps heat. We know this. We're living it. So slowly, over millions of years, the CO2 built up, the heat built up, and the ice finally started melting. Darker ocean and land got exposed, which absorbs even more heat, which melted more ice. The same runaway feedback loop that froze the planet eventually ran in reverse. Volcanoes saved the world. But the world that emerged was fundamentally different from the world before. The atmosphere now had oxygen. Not as much as today. That would take another billion years to reach modern levels, but it was enough to change everything. The survivors had new capabilities. Aerobic respiration gave them access to way more energy. This would eventually enable larger cells, more complex processes, and way down the line, things like muscles and brains and things that require a lot of energy. The oceans were different too. The dissolved iron was gone, rusted and buried. The water was way clearer. This gave rise to new chemistry that was possible. And those banded iron formations, they became one of our main sources of iron ore today. The rust of an ancient apocalypse became the material we use to build skyscrapers and cars. You are surrounded by atoms that were first touched by oxygen 2.4 billion years ago and now repurposed. Old rocks seem a bit more interesting now, right? So the Great Oxygenation Event is one of the most important events in the history of life on Earth, and we, barely talk about it. It shows us that life can transform a planet. All right, so let's do a checkpoint. Let's make sure we got this. Before oxygen, Earth's atmosphere had almost no free oxygen. Life was anaerobic. The oceans were full of dissolved iron. Cyanobacteria. It figured out oxygenic photosynthesis, splitting water with sunlight. Super efficient. It produced oxygen as waste. The delay. For hundreds of millions of years, oxygen was absorbed by dissolved iron in the oceans. Banded iron formations are the evidence, ancient rust. And here's the tipping point. Around 2.4 billion years ago, the iron sinks filled up. Oxygen accumulated. The Great Oxygenetic Event began. Now, the catastrophe. Most anaerobic life went extinct. First mass extinction on Earth. Oxygen was poison. Then came the snowball Earth. Rising oxygen destroyed atmospheric methane, reducing the greenhouse effect. The planet may have frozen over. Now, the survivors. Some hid in oxygen-free zones. Other evolved defenses, and some learned to use oxygen. Aerobic respiration, 16 times more efficient than anaerobic. It's like $32 an hour versus $2 an hour. This is the new world. Oxygen, atmosphere, new capabilities, the foundation for everything that came after. So there we have it, the conclusion. So 2.5 billion years ago, cyanobacteria started dumping their waste into the environment. That waste, oxygen, poisoned most life on Earth, possibly froze the planet and transformed everything. The survivors who learned to use oxygen instead of being killed by it gained a massive advantage. Aerobic respiration unlocked energy reserves that anaerobic life couldn't touch. This set the stage for everything that came next. More energy means more possibilities, larger cells, more complex processes. Eventually, a billion years or so later, the rise of eukaryotes, cells with nuclei and organelles. But that's a story for next time. For now, take a deep breath. Feel that oxygen entering your lungs. That oxygen is the legacy of ancient bacteria, the waste product of organisms that had no idea what they were starting. You're breathing the apocalypse, and that's keeping you alive. So, quick optional end note before we go. Quick update on something we covered in episodes 1 and 2. Do you remember the RNA World hypothesis? The idea that RNA came before DNA, before proteins, before everything, and that it had to figure out how to copy itself with basically no help. Now, remember me saying everything I'm saying is a hypothesis. that we're piecing together a forensic scene that happened billions of years ago, so hypotheses can change. But the RNA World hypothesis just got an update that is making it even more likely. Because one of the biggest criticisms of that idea has always been, okay, yeah, RNA can fold up on itself, and theoretically, it could copy itself, but it's so fragile. How does this tissue paper molecule hold together long enough to actually do it? Well, in February 2026, yes, this February, a team at Cambridge published a paper in Science, that's a big paper, describing a tiny RNA enzyme. They call it QT45. Quite tiny 45, which is adorable. And it can copy itself and its complementary strand. Not a protein doing it, RNA doing it to itself. It's slow, it's messy, it's not a full replication cycle yet, but it happened. And that's a huge step forward. And here's why that matters. For decades, the knock on RNA World was that a self-copying RNA molecule would be too big and too complex that it couldn't just show up on ancient early Earth. QT45 is tiny. It's like a Post-it note. It was thought something this small couldn't replicate itself, but QT45 did. And it's small enough that it actually could have emerged from a primordial soup spontaneously. Which means the question just shifted from, is this even possible? To, under what conditions did this happen? That's a massive shift. The bridge from chemistry to life just got a little sturdier. And I think that's a pretty good place to leave things for now. All right, now we're done. Thanks so much for joining me on this biological journey. I'm Jackie Mullins, and this has been From Cells to Us. How? I'll see you next time.